practice more, let's set up an integral for the volume of the solid region inside the cylinder x squared plus y squared is equal to 4 and bounded by the plane z equals 0, so that's the xy plane, and the hemisphere z is equal to root 9 minus x squared minus y squared. Okay, and we'll do this both in rectangular coordinates again and in cylindrical coordinates. Okay, might as well draw a picture, right? X-axis, y-axis, z-axis. So there's a cylinder here. So there's, a bunch of circles stacked right on top of each other of radius 2, I guess, right? Because x squared plus y squared is equal to 4. And then we're supposed to cut this with just this plane here. So there's sort of this one final circle at the bottom here. Okay, and then there's also this hemisphere of radius 3. So, okay, so it extends beyond this a little bit, yeah, but we've got, this, whoops, let's just go ahead and draw that circle all nice first. Let's try that again. There we go. So there's from 3 to 3 here, that's behind there, and then there's this, it goes up like this, and it ends up intersecting. That's probably not the best picture. Trying. These are hard to draw. Like that. So there's this top part there, sort of a spherical like cap on top, and otherwise this tube underneath. Okay. So what we're seeing here is that z is bounded between 0 below and root 9 minus x squared minus y squared above. Okay. Then when we end up eventually projecting this to the xy plane, well, yeah, sure, there's this sphere of radius 3 out here, but that's not, if we look at the filled-in solid part of this thing, it's really all constrained by this tube of radius 2. Yeah, so when we project, we're really going to be down to this radius 2 in the xy plane, and so we'll have this solid filled-in thing. And so this should inform us how we'll set up the integrals. So again, we'll just integrate the function 1. So let's go with dz dy dx in rectangular coordinates. So from up here we have integral from 0 to root 9 minus x squared minus y squared. And then once we project it down, kind of usual game at this point, so negative root 4 minus x squared. Let's write that a little cleaner. Negative root 4 minus x squared there, all the way up to positive root 4 minus x squared, and then finally the x bounds need to go from negative 2 to 2. Okay, if we set this up in cylindrical coordinates, so the dz dy dx is a dv, so that's going to come with an extra r now, and we'll have r times, and let's stick with the order dz dr d theta. Z should still start at 0, but then what it goes to, we'll write this as root 9 minus r squared. And then once it's projected down, we have this thingy again. R goes from 0 to 2, and theta goes from 0 to 2 pi. The real point of all of these, why we keep doing these in both coordinate systems, is to say, yeah, you can do it this way, but it's a little much, isn't it? For these shapes that have a lot of roundness to them, this thing in cylindrical coordinates is just kind of a lot nicer. It's a lot more natural to do, right? Okay, let's do the following. Let's rewrite the integral 0 to 2 pi, integral 0 to 2, integral 0 to 5 minus r cosine theta minus r sine theta of r to the 4th sine squared theta cosine theta dz dr d theta as a rectangular integral. So can we rewrite this triple integral that's currently in cylindrical coordinates and instead write this in xyz coordinates, in rectangular coordinates? Well, so we're just trying to build backwards from the kind of thing that we did. And if we look at the bounds for r and theta, we really see here that in the end, the projection onto the xy plane really is supposed to look like this, right? It should be, let's see, 0 to 2 pi, so all the way around, 0 to 2, so radius 2, it should be this, let's draw it a little better. Yeah, it should be this filled-in circle of radius 2 on the xy plane. Okay, so that's what we should get in terms of understanding the region. Finally, looking at this right there, the z bounds, we see 0, that's not going to cause us any problem. And then it goes up to 5 minus, well, r cosine theta would be x, and then minus r sine theta would be y. Okay, so that's relatively easy to understand. And then the point is really just maybe we should note that z equals 5 minus x minus y is a plane. Right? In fact, so yeah, the equals version of this, meaning we should, I think, probably be looking under a certain plane. And that plane, by the way, if we just rewrite it, x plus y plus z is equal to 5, has normal vector 1, 1, 1. Okay, so here's what I'd like to do. I'd like to take the integral that's up here. Sorry to rewrite it. Integral 0 to 2 pi, integral 0 to 2, integral 0 to 5 minus r cosine theta minus r sine theta of r to the 4th sine squared theta cosine of theta dz dr d theta. And I'd like to actually just rearrange some of the things here. You'll notice this r to the 4th. And so this next step is not really actually calculus or trigonometry or much anything, just kind of algebra to kind of regroup some things here before we really get started. So integral 0 to 2 pi, integral 0 to 2, integral 0 to 5 minus r cosine theta minus r sine theta as before. Now, let's reorganize this integrand. Instead of r to the 4th, I'd like to split it up as r sine theta quantity squared, and then have an r cosine theta. Now we've covered 1, 2, 3 of the r's. There's one final 4th remaining r. Good thing. We have r dz dr d theta. Now it's all of that. Okay, now all 4 factors of r have been accounted for. It's this part right here, underlined in green squiggle, that's going to be dv. So that would be what turns into dx dy dz or dz dx dy, or whichever order we choose to go with. Okay, so we'll have integral, integral, integral. It is, generally speaking, when converting back and forth, can be helpful to have dz as the first variable in the order of integration. And let's just go with dy dx. I think either order will probably work out okay. And then the point is the rest of this stuff here. So r sine theta quantity squared, and then times r cosine theta, that should turn into, well, y squared x times x, right? So r sine theta turning into y, r cosine theta turning into x. And then if we look at the bounds for z, well, we can kind of basically read them off. It should be integral from 0 to 5 minus x minus y. And then the point is, once you've projected down, it's this information that we saw already over here. You know, had we been setting up this integral ourselves in the first place, to figure out what would have went here, we would have been projecting down and getting this picture. So we just need to describe this now in rectangular coordinates. We've done this a number of times now. So if x is fixed, fixed x value here, then we're going from that y value up to that y value. And so we'll have here negative, let's move the integral signs a little bit here. So we should have the y integral going from negative root, let's see, radius 2, right? So yeah, root 4 minus x squared all the way up to positive root 4 minus x squared, and then projected onto the x-axis, the x values go from negative 2 to positive 2. Okay, so maybe it will help just to underline this in green. Yeah, so that part here is dv, just like over here this part, that was also dv.